Hello, everyone. First of all, I want to say thank you to the organizers of the symposium for inviting me to give this talk. I feel really honored. And well, when they invited me, I also thought, oops, I got at that age where they invited you to special talks. But anyway, I'm very happy to be here. Well, actually, to be recording myself, which is always a bit weird. So, today I would like to talk and make few reflections about the family Teloschistaceae. For those expecting new update proposal on genera classification, you can disconnect. I'm not going to give any new solutions for that problem. I'm aware that there has been some recent heated debate in social media. I saw Pierluigi saying the Teloschistaceae are a nightmare. Yes, they are a nightmare. And today I would like to explain to you maybe why a nightmare and complex and maybe a bit more difficult to categorize than other families of lichens. So I'm going to take you into a journey, the journey I went through trying to understand this group. And just a quick reminder, the family Teloschistaceae is classified within the order Teloschistaceae. As you know, the estimate of number of species ranges between 800 and 1,000, and I think this is probably an underestimate of the real diversity of the family, with a Teloschistaceae type ascus, and the typical with most species with typical spores with equatorial thickening, and many taxa with anthraquinone pigments in some part of the talus. And this is a family that we can consider cosmopolitan, but has taxa, or is especially associated with exposed habitats, and is able to colonize, some of the representatives are able to colonize some of the most arid regions of the world. When I started studying the group in the almost pre-molecular era, I could happily put together this nice summary of the most up-to-date and revision of the most up-to-date genera classification of the family, with, for example, the most recent revision with 12, including 12 genera, and with Caloplaca as the most species rich genus. As you know, this is not the case anymore. But from that time, I would like to highlight, especially for the maybe the most young generations might not be aware of this piece of work from Karnefeld in 1989, which for me is the first attempt of an objective genera revision, simply using morphological, anatomical, and cladistic approaches. And even with limited characters, I think it includes a very thorough revision of the general diversity, gives you a glimpse of the general diversity of the family. I found very useful at the time, and sometimes, and still now, I go back to for refreshing. So when I started, I focused on the genus Caloplaca, and in particular into tiny group of species that was called at the time the Caloplaca saxicula group, now recognized as Caloplaca genus. And yeah, happily went out collecting samples and trying to understand the main characters of this group of species, different tinges of orange, characteristics of the lobes, the lobation, length of the lobes, all types of macroscopic characters, diversity of areoles, diversity of the apothecia, vegetative structures, if they were present or not. And I also made lots and lots of drawings. And I would like to say, I know that right now many people have time limitations, but I still find very useful to make drawings on top of taking good images of microscopic characters, because it's while drawing I found and spotted the differences in between the different species and taxa. And here a few examples of the characters I looked at the time, the types of cortex structure, ASCII, and different characteristics of the paraphysis, for example, anatomy of the paraphysis and the apothecia. I drew and measured lots and lots and lots of spores with different features in the equatorial thickening, and with all of that, I came up with new species and new taxa, and obviously I added molecular data. I reconstructed the relationships of these morphospecies that I was describing, and looked for correlation with molecular data. And most importantly, I want to highlight here is that I was looking at a tiny group of species, but at this stage I had already explored most of the characters that you can find in this family of lichens. And that's what happened with Teloschistaceae. We don't have that many characters, a few macroscopic characters, some microscopic features, but at family level, there's not much more. Different types of growth forms, not much more. But all these characters, and I think this is very important, especially for field lichenologies, all these characters are useful at species level. If what you want to do is identify diversity for this family, all these characters are reliable, and they can bring you to identify species using identification keys easily. And that doesn't only work for the Caloplacus saxicola group. You can find multiple examples in the literature. For example, Bondrak and colleagues have published multiple reviews of different species complexes and particular genera within the family, where all these characters, the combination of all these characters, allow you to identify nicely species units. And this is usually supported by molecular evidence. There's a particularly a nice review on the main characters, morphological, phenotypical characters that you can look into the Teloschistaceae by Bondrak et al. From 2013. But for those starting in the group, it's quite useful, and to know how to measure the different traits and how to identify the different structures. So anyway, following on my journey, what happened next? I was looking at the Saxicola group. I had this general view of the main characters of the family, but obviously I had to confirm that the Saxicola group, or Ester Gaya, was monophyletic, and for that I had to reconstruct a whole phylogeny of the whole family that at the time was based only on ITS. I want to highlight something that recently Robert Looking has gathered all the ITS from Teloschistaceae available and reconstructed a phylogeny, and he was surprised that the amazing phylogenetic resolution you get for this family using just this locus. And I don't think that happens with all groups of lichens, but it's quite striking, and obviously it's not ideal, it's not perfect, but to have a first glimpse with ITS, you get quite a lot of information at that phylogenetic level. So basically, as you know, at the time when we started building these ITS-based phylogenies for the family, we found that most classic genera were polyphyletic. Luckily, my Saxicola group was monophyletic. And not only the genera, but some of the species complexes that, for example, traditional literature like Clausade and Roux had used for a long time, and they were very useful for assessing diversity in the group and identifying different units like these species complexes described by Clausade and Roux were all polyphyletic. So nothing was useful at the time, and several authors came to the same conclusion. And obviously, there has been several attempts to fix this solution, to find a solution for this situation, to fix kind of mess at genus level. And there's one classic, almost classic example of the revision of the classification of the family by Arup et al. In 2013, where using mostly monophyly as a criterion, but also combining, when possible, some morphological and ecological characters, they came up with an update of the classification with 39 genera and basically 31 newly described or resurrected genera. Following that, there has been several other publications in most recent years that are mostly focusing on mostly regional, focusing on particular areas in the world. And what I want to highlight here is that in this, and especially I put two examples that are from South America. What happens in the family, and that's what I think highlights the fact that I think we still haven't sampled the whole diversity, or even like half of the diversity of the family, is that every time a new area, a new region is explored for Teloschistaceae, new lineages appear. And these are deep, long branches that are not related, phylogenetically related to any other existing lineages. So basically, every time someone goes collecting and identifying new taxa for the family, these new taxa, when they are sequenced, they don't fit in the already existing clades. They are reconstructed as new lineages. And as I said, usually they are quite long, deeply rooted branches, which it could be, as I said, due to an undersampling of the group, that there's still lots of diversity that hasn't been discovered. Also could be that these branches are relics of all groups, or that we are seeing evolutionary stasis, which I find less unlikely, but it could also be possible. But what is the solution for this? What people are doing basically is try to name this in accordance with the current classification, new genera for these new branches, new lineages. But this has reached, I find, in a way, an extreme situation with far too many genera. Some of them lack actual evidence, phylogenetic evidence, and basically what I find is that yes, we need to accommodate these new lineages, but we can't be describing genera for every single new branch we find. So we need to find a balance. We need to find an intermediate solution to this. It's true, we cannot use the old classification, but we can go that way and describe every single branch as a new genus. And this is, I think, is nicely summarize this situation by this plot that when I convinced my student Theo to get involved into this family, the first thing he did was to plot some of the larger families of lichens against number of species against number of genera, and as you can see, he came to me saying, wait a moment, excuse me, why Teloschistaceae are up there? Well, actually, with the new synonymizations, it should be below 100, but still, yeah, it should be somewhere around here. Look, we have Carafidaceae, Parmeliaceae, even Carafidaceae sensulato, but even these two families with the largest number of species, they are down here. This is not acceptable. This is not real. And I have to admit that at some point, when all this explosion of new genera started, and the classification continued evolving, I got a bit kind of saturated about Teloschistaceae names, and I shifted slightly to trying to understand the evolution of the group, of the family. And I said, okay, yeah, we have few characters, but maybe trying to understand how these characters evolve, how they relate to each other, combining them, maybe they help us to understand a bit better what's happening with the group. And maybe, yeah, understanding the evolution of the family may tell us why we end up with a plot like this, which doesn't make sense to me. So yeah, I went back to the phylogeny and focusing on the family, I said, okay, let's try to reconstruct at least the evolution of some of the main traits, or at least the traits that I thought that might be more important, and investigate the correlation between them and see what was the role of these traits in the history, in the evolutionary history of this family. For that, I counted with the invaluable help of Samantha and Reynaldo, which helped me to gather all the phenotypical data for a subset of representatives, representative taxa for the family, and we categorized in different main groups. So, and we used this data set of phenotypic characters, as I said, to understand the evolution, the relationships, and to see if we found some solution to the classification. And as I said at the beginning, we didn't find the final solution, but I think we squeezed the data as much as we could. First of all, so one thing, we usually in talks, we usually show the nice results and the beautiful things that we can publish. Today I'm showing some slides that I haven't published because they were not useful, but I want to show you all the effort we've done to try to categorize this group. And how difficult it is. It's like, oh, when Teloschistaceae people are crazy, and no, it's just we are trying, but it's not that easy. And I want to show you that today. Okay, so with that phenotypical matrix, one of the things we did, we tried to use different clustering methods to try to see if by clustering some of the characters would correlate with some of the already defined genera or new genera. It kind of didn't work. We also this structured some of the traits and look at the phylogenetic distribution using maximum likelihood methods, Brownian motion, and look, for example, to the evolution of anthrachinons and see if there was any patterns. We know that some of these traits are like growth habits. They have a high level of homoplasy, but still maybe they have also phylogenetic signal, and this phylogenetic signal maybe can be translated into the classification. Complicated, as you can see in these examples that I'm showing, and this is more combined the different states for the anthrachinons, growth habits, and also ecology. So these figures are interesting for me, very interesting in terms of evolution, but not for the practicality of genera delimitation, which, as I said at the beginning, for me the two things go a bit together. Because they explained each other. Why can't we solve the classification? Well, because maybe the evolution of the main traits of the family was complicated. The other thing we did was look at the evolutionary relationships between the phenotypic traits in the context of correlation networks. And this approach is quite interesting because basically here we said with the help of Robert Lachlan, we said, okay, let's see how they are linked with each other and which traits might be more important, may show higher correlation with the other traits in our network, and might be more widely distributed across our phylogenetic tree as well, because these traits, a change in some of these more highly correlated traits, a change in these traits might involve and cascade into changes into other traits, and basically affect more greatly into the evolution, into the general evolution of the family, of the group. And yeah, we found some traits that I highlighted in this little square here. Some traits were more central, for example, anthracynonans in the thallus. And yeah, we also looked at network centrality that confirmed these higher highly correlated traits. So having that in mind, having a subset of traits that seem to be more important in the interaction with the whole landscape of phenotypical characteristics of the family, but also into the general evolution of the family, we moved into looking into particular evolution of the group. First of all, we didn't even know where when the Teloschistaceae had started diversifying. So first of all, with the help of Cecile Gedan, we dated the phylogeny of the family. So basically, the Teloschistaceae started diversifying about 100 million years ago, and using phylogenetic and comparative methods, we established that around that time, around 100 million years ago, the family underwent a shift in diversification rates, a jump in diversification rate along the root of the family, and after that, the higher level of diversification then continued to increase, but more gradually until the present day. So with that, we try to find correlations with some of our central traits, and we performed binary ancestral reconstructions, multi-state reconstructions, and we came out with the paper from 2015, where we assessed that the family might have undergone an adaptive radiation beginning at the onset of the diversification of the large Teloschistaceae family, associated with a shift to sunny, rocky habitats, and also associated to the innovation of using anthracynons as a sun-protecting pigment. And the question is, why then? There are two things here. Why then, and also the fact that people talk about this, the key innovation, the anthracynons. Well, it's not only anthracynons. The most interesting thing here, and that it happens with other groups of lichens. It's difficult to find one single trait that especially biological trait that may trigger a diversification spur or an adaptive radiation. What we found here, and it's been found in other groups, is that there is an interaction of multiple biotic and abiotic characters, and this interaction of multiple characters is what triggers this sporin diversification and this pattern. And these multiple biotic and abiotic characters are the ones that we found in our initial correlation networks nicely. Now, this model is quite simplified. Obviously, there has been transitions and reversals. We have, especially within the Caloplacoideae. And down here you can see that this is loss of anthracynons and also reversals into epiphytism as well. For example, the Gaya lineage. Recently, we have found that bone drag sampling areas that had never been sampled, like in Asia. This group that was usually considered as a saxiculous group now has representatives that are mostly epiphytic. So the story is more complex than this simple figure, but At the onset of the family, it seems quite clear that this increase in diversification linked to these various biotic and abiotic factors. As I was saying, that's, again, these are all hypotheses, and there can be, as usual, multiple explanations. One of the things is, this starts happening in the early Cretaceous, and several events seem to concentrate around that time. And for example, one explanation could be that an increase in temperature could have led to the colonization of newly formed arid and exposed regions. And that would be possibly augmented also by greater provincialization and also changes in the orographic landmarks, for example, the separation of America and Africa. Another alternative could be later on with the subsequent increase in seasonality and spread of decidiousness in both angiosperms and gymnosperms. In a posterior cooling period, they may have changed a light change in light environment, and the ancestors of the Teloschistaceae, the epiphytic ancestors of the Teloschistaceae, might have had to adapt to higher light exposure. And then in this later scenario, who knows, maybe an intermediate light exposure offered by deciduous habitats might have acted as a stepping stone towards more exposed habitats, and also towards the evolution of the light protective anthraquinone pigments. All these are hypotheses and equally possible explanations, but the beauty of it is that we can now draw some of these hypotheses and make some of these assessments, and this is thanks to the development of new phylogenetic and comparative methods that until now we didn't have, and without a proper fossil record. This type of hypotheses were basically relegated to paleontology, but now. And mostly it has been in the last 5 to 6 years that we have been able to implement some of these methods, and now new methods, because, for example, for correlation, to test for correlation of characters, we can use new methods like STRAP, etc. But all these new methods that actually are still in the process of development are allowing to place lichens in the big picture of macroevolutionary dynamics. And it's not only for Teloschistaceae, it's for many other groups. And the niceness of it, maybe we are drawing this hypothesis, and maybe we're making wrong estimates of diversification or timing, etc. But what is nice that we can assess it, and we can still attempt to draw some of these hypotheses and draw conclusions out of them. Here I put a few other examples. For example, a few years ago, there was this similar study on the families, Sensulato family Graphidaceae, because now it's been split, and the Parmeliaceae. And it was beautiful to see that Parmeliaceae had a quite similar pattern of diversification as in the Teloschistaceae, with some lineages like Parmotrema having a similar adaptive landscape and diversifying into probably more arid and exposed rocky habitats, as in the family Teloschistaceae. We have found also, we could test also other examples of key innovations, like, for example, the columella in some of the lineages of the Graphidaceae, like Inocellularia. Or this other recent study that has compared different families of lichens, testing that, again, diversification rates, and kind of hinting at a potential correlation with the macrolichen state, Not for all the families. For example, unfortunately, they didn't find a correlation with Teloschistaceae, but for some others, it seems to have some type of correlation with increasing of diversification rates and the macro lichen state. But so all this is very beautiful, and as I said, yeah, we have new tools that help us to understand the evolution of lichen forming fungi and lichens in general. There is also this beautiful study from Nelson et al. From last year. But going back to our initial issue about genera, numbers of genera in the family Teloschistaceae, when you look at this summary tree, here you have the Teloschistaceae. Here you have, for example, as an example, the family Parmeniaceae. Teloschistaceae have lower diversification rates than Parmeniaceae. They have lower number of species. So from an evolutionary perspective, from a biodiversity perspective, they have lower numbers. We can't have this picture. If we want to be more realistic, I think Teloschistaceae should be more at this level. I know that some people will still say, "Oh God, you want 50 genera?" Yeah, I mean, we have to find the balance because I plotted here in this circular tree of the family the old colored the old genera, different colors: Caloplaca, Teloschistaceae, Xanthoria. They are polyphyletic. We can't go back to that. Well, maybe someone will be happy saying, "I want a Caloplaca macro, the whole family, one genus." And we solve the problem. Yeah, we could. Yeah, but do you want to transfer all Teloschistaceae into Caloplaca or whatever genus name we choose? We have to be realistic. We can't go back to the old classification. We can't have 100 genera, but we have to find something something in between. So what's next? What's next? As I said at the beginning, I'm not gonna give you a final solution, because I think we are working on it. But there's some options and some methods that can help us and can guide us a little bit on this endeavor. So, one of them, for example, my student Theo, with the help of Pierre Lepogam, is revising thoroughly the chemistry of the family using mass spectrometry and trying to build molecular networks that again can use a bit the same approach as I use for the other phenotypic traits, and that you can incorporate phylogenetic dependency. And yeah, someone will say, "Oh, we already revised and the chemistry, it doesn't work, is not useful taxonomically." Yeah, but we can look at it again with different eyes, and we can revise it, and these molecular networks give us another level of information that we didn't have before. And one thing is, they haven't been used actually for lichen, to study lichen metabolomes. And whilst taxonomic data have been superimposed onto some of these networks, we haven't tried the opposite, to use the networks themselves to try to delimit some of the taxa. And in the first survey, this is still work in progress. This is part of Theo's thesis. We already found some genera. Some of the newly described, actually newly described genera, showed signs of chemical distinctness using this approach. So I think I'm quite hopeful It's not going to work for everything, but it can reinforce the delimitation of some of the already existing or delimited and described genera, or we may find a new trait, chemical trait that may support some delimitations that didn't have any phenotypic trait to support that. Still, I understand that a molecular network based on mass spectrometry might not be very useful for someone working in the field, but at least it's something that is meaningful and that gives some more support to the hypothesis presented at the level of general delimitation. Another thing that we are looking into is using more methods. So we use new methods to understand how phenotype characters relate to each other. We use methods to understand how they evolved and how they correlate with branching patterns, with the diversification, speciation, extinction rates in the family. Now, we can use other methods to try to delimit units. And these methods try to be more objective, but we need to remember, and we have to keep this in mind, all the evolutionary research we're doing has a certain level of objectiveness, but for me, from my personal perspective, and many other people, we understand that there is no clear definition of a genus beyond a monophyletic group of species, and these groups may share phenotypic characteristics, geographical distribution, ecology, but sometimes they don't. And we can try to apply some of these more objective approaches, but still they won't give us the final solution, because what we are trying to delimit is not a totally natural unit. Species are natural units from my perspective, but genera is a communication tool. We want to be able to communicate. We want that when people go into the field, they can put names into things. As I said initially, don't despair, because for me, the most important thing, if you want to assess the diversity of an area, for Teloschistaceae, you have very good morphological characters that work at species level. And for me, that's essential, and that's basic. Now, if you can't do it in the field, maybe you will have to go home and buy a bentos lab, portable bentos lab or something, sequence ITS, and then come up and put your sample in a phylogeny and get a genus name. You will have to find intermediate solutions. But sorry, I got distracted. Going back into trying to use slightly more objective methods. In this example, for example, we tried GMYC, which is a method that uses coalescent theory to search for groups of taxa, these different groups of taxa have alternating different colors in here. Looks for groups of taxa separated by long internal branches, followed by an increased branching rates, like here or here, for example, or we found it here or here. And this this method was described by Barraclough and also, if I remember, Humphreys and Barraclough, and they considered that this they identified evolutionary processes that act on these groups, meaning that the genera designated using GMYC may be a bit less artificial than more classically described genera. But as I said, is the concept of genera the problem for me. But anyway, you can I think it's interesting to test these methods, especially with a group like Teloschistaceae. In this case, using GMYC theory and the analysis, we found 18th units. We also tried temporal banding. As you know, temporal banding has a higher element of subjectivity because it basically you fit into a classification. In this case, we tested it using the old classification and also the Arup et al. Classification. With the first one, it gave us 24 units, and with the Arup et al. Classification, it gave us 35 units. So basically, well, with temporal banding, what you basically you for those that haven't used it, you basically draw a cutoff from where all taxa identified with a specific rank are considered to evolve together, and that's where you establish, for example, the genera delimitation, but you could use it also for family delimitation. So as you can see, we got very different units assessments with the two different methods, but also with the temporal banding with different classifications. So what do you do with 18, 24, or 35? That's a challenge. But I think, again, use more characters, test these methods, incorporate all the information, and then maybe we can come up with a final assessment. Another option that has been tested recently by Karina and Robert looking is this phenotype-based phylogenetic binding method, where you combine morphological matrix or phenotypical matrix and also and the molecular data, and use EPA evolutionary placement algorithm analysis. And for this, with this approach, the niceness of this approach is that even for taxa for which you don't have molecular data, you can use your backbone tree and place on data with taxa with only morphological data into your phylogeny, which is can be useful. So this is where we are. We can incorporate or assess new traits. We can test new methods and come up with the best solution. But I tell you, it will be a solution that won't please everybody. We can go back to the beginning, but we cannot accept 100 genera, as I was saying. We have to be sensible and use as much solid evidence as possible. And I would like to say thank you to many people, because this talk was I actually got a bit in panic when I prepared this. Like, oh no, I felt a bit like an old lady there, but using all the slides, and actually summarized all the work I've done on lichens since I started. And I owe a lot to many different people, from my supervisors, PhD supervisors, Xavier and Pere Navarro Rosines, that show me how to draw all those beautiful schematic drawings. All my mentors, Francois Luzzoni's group in doing my postdoc, and many other people that have helped me developing and testing new methods, gathering data, collecting all the collecting trips without help of many people. And I'm missing probably many names in the list. Help me collecting and having fun working on this difficult but fantastic and super exciting and interesting group of lichens. And obviously, as always, without money we are nothing. And I put some of the main sources of funding below, from Q and Education and Evolutionary Education Trust and many others, NSF. And I hope you enjoyed this talk, and I hope I didn't say many silly things. Just a note, I read an article saying that women giving scientific talks that make a lot of jokes are taken less seriously. And I thought, oh, maybe that's, I understand many things. So I try to not say many jokes during this talk. I hope that you enjoyed it. And I'm happy to take any questions.